Hi and welcome to this second video of my playlist about the best methods to convert amides into ketones. In this presentation we'll have a look at the use of ionic enolates as nucleophiles. These would be, for instance, lithium, sodium or magnesium enolates of ketones, esters, amides, sulfoxides and related compounds. Like in the Claisen condensation of esters, enolates act as nucleophile while the metallic cation simultaneously activates the amide as Lewis acid. Once the new carbon-carbon bond is formed, a metal amide must be eliminated from the intermediate metallated hemiaminal. Because most metal amides are strong bases and nucleophiles, metal amide formation does not always occur readily, and metallated hemiaminals tend to be more stable than metallated hemiacetals. If metal amide elimination occurs, the newly formed ketone will immediately be deprotonated by this amide, also because 1,3-diketones or 3-ketocarboxylic acid derivatives are strong carbon acids. The new enolate is only a weak nucleophile and a poor electrophile and does not usually react with any of the starting materials. Most amides are too stable and do not react with simple enolates. Some exceptions are imidazolides, N-aryl amides, Weinreb amides, and imides. Also amides of exceptionally strong carboxylic acids, for instance trifluoroacetamides, formamides or oxalamides, are more electrophilic than amides of less electron-deficient acids and do react with enolates. Then, some enolates may be destabilized somehow, and stronger bases than usual will be required for generating them. These include, for example, cyclopropyl ketone enolates, acetoacetate dianions, beta-lactam enolates, and bridgehead enolates. The suitability of amides as electrophile can be enhanced by conversion into iminoethers by alkylation or into iminosulfonates by sulfonylation at oxygen. Alkylation requires hard electrophiles such as dialkyl sulfates or trialkyl oxonium salts, in particular if the amide has nitrogen-bound hydrogen. Iminoethers or sulfonates are often more electrophilic than esters and readily react with a variety of nucleophiles, including weak carbon nucleophiles such as malonates or 1,3-diketones. The enaminones resulting from reaction with a ketone enolate are more stable than simple enamines but can still be hydrolyzed to the corresponding ketones. Just to show you how unreactive amides are. When dilithiated N-methylbenzamide was treated with an excess of NMP, no addition to the NMP carbonyl group, but mostly metallation of NMP occurred. The lactam enolate is quite stable at low temperature and dimerizes only slowly. Such amide dimers are rarely prepared under basic reaction conditions, but are more readily accessible under acidic reaction conditions, for instance by treatment of an amide with phosgene or phosphorus oxychloride. There are some examples in part 3 of this playlist. Let's have a look at some specific examples. Morpholides are more electrophilic and better suited for the preparation of ketones than simple dialkyl amides. Reaction with the enolate of Weinreb acetamide, however, only reached about 70% conversion after 70 hours at -50 degrees Celsius. A higher reaction temperature could probably not be used here because this would have caused ring opening of the oxyrane. The enolate of butyl acetate, though, was sufficiently nucleophilic to be acylated by a morpholide at low temperature. Neither racemization nor epoxide cleavage occurred. Butyl acetate was chosen here because it is less volatile and can be dosed more accurately than ethyl acetate. Formamides are more electrophilic than other amides and can sometimes be used to formulate enolates. Alpha-formyl ketones or carboxylic acid derivatives, though, are highly enolized and sensitive and readily oligomerize. Treatment with weak nucleophiles can also cause rapid deformylation, in particular if the aldehyde is not enolizable. In this example, lithiated lactam was treated with an excess of DMF at -20 degrees Celsius for 2 hours, and a good yield of alpha-formyl lactam was obtained. Also Weinreb amides are more reactive than simple dialkyl amides. In this example, the Weinreb amide of hexanoic acid was used to acylate lithiated ethyl acetate. After 5 hours at -78°C, the conversion was not complete, but a reasonable yield of ketoester could be isolated. Exceptionally nucleophilic enolates do sometimes react with even weak electrophiles, such as simple amides. Here the dianion of methyl acetoacetate was condensed with dimethylacetamide at 0°C. The addition of an excess of boron trifluoride etherate lowered the amount of byproducts and, despite stabilizing the nucleophile, led to a good yield of tricarbonyl compound after only 2 hours. In this example, an aziridine-derived amide enolate underwent self-condensation at room temperature. Such Claisen-type self-condensations of amides are rare, but in this case the enolate was particularly reactive. Delocalization of the anion to the carbonyl oxygen atom, which is the main reason for the CH acidity of amides, implies here the formation of a highly strained methylene aziridine. Whenever the enolate resonance structure with the charge at oxygen becomes too strained, the nucleophilicity and basicity of the enolate increases. Methylated DMSO is not very nucleophilic and only reacts sluggishly with DMF at room temperature, as shown in the first equation on this slide. With the more reactive N-formyl form anilide of the second equation, however, a high yield of the sodium salt of formyl DMSO was obtained. N-ethyl acetanilide again reacted more slowly, and even after heating for 2 hours, only 38% of product resulted. Amides can also be activated by acylation or alkoxycarbonylation at nitrogen. In this example, the lithium enolate of benzyl acetate was acylated by an N-Boc pyroglutamate at room temperature. The imide was more electrophilic than the ethyl ester and reacted selectively at the acyl group, not at the terz-butyl carbamate. In this example, a Boc-glycine methyl ester acylated at nitrogen was isomerized by treatment with a strong base. DMPU was used as catalyst or to enhance the solubility and reactivity of the lithiated intermediates. Such acyl migrations may occur intramolecularly, but could also be intermolecular reactions. So, what else can go wrong? Even after complete deprotonation by an excess of a strong base, ester or ketone enolates may undergo self-condensation. Here, for instance, the Weinreb amide was too unreactive, and only the Claisen condensation product of the ester was obtained. Non-enolizable aldehydes or ketones with electron-withdrawing groups in alpha position are readily cleaved by nucleophiles. Such products must be isolated carefully, because otherwise deacylation may occur, as in this example. Here are some more, mostly recent examples, for further inspiration. You can also find this list in the description of this video. The next presentation of this playlist is about the preparation of ketones from amides under acidic conditions. For some types of product, acid-mediated condensations are easier to perform and give higher yields than condensations in the presence of bases. So don't miss it.